be a talk by Professor Ken Golden from the University of Utah. And Professor Golden is currently a professor of mathematics and adjunct professor of bioengineering at the University of Utah. He graduated, received his PhD in mathematics at the Quran Institute at New York University in 1984, and then in 2011, Professor Golden was selected as one of the fellows of the Society for Industrial and Applied Mathematics, and just this year he was in the inaugural class of the Fellows of the American Society, and we are very pleased to have Professor Golden come and speak to us on his mathematics in the melting polar ice cap.
Well, thanks very much. It's certainly a pleasure to be here, and thanks to some for inviting me. The evidence is clear. Our climate is changing, and it's changing perhaps most rapidly in the polar regions. And I'm going to be telling you about how we're using mathematics to try to understand our climate system better and ultimately to try to improve our projections of climate change. And so this first picture here, so we've been down to Antarctica and up to the Arctic many times. I've actually been to Antarctica 7 times and the Arctic 8 times. In fact, I'll be going in about a month back to the Arctic again. And so you'll see lots of photos from some of our polar expeditions. This first shot is from Antarctica, just from several months ago, back in the fall of 2012. And you'll be seeing at the end, you'll be seeing a video on this most recent expedition. So okay, so what are we talking about? We're talking about the cryosphere. The frozen portion of Earth's surface. This is the southern cryosphere, consisting of 2 main parts: the great land ice sheets, which is snow building up over millions and millions of years and forming glaciers, and then flowing out to the sea. But what we're interested in is the frozen seawater, the frozen ocean water out in the fringes here, which is called sea ice. And actually, so I've been into the Weddell Sea and the Ross Sea, and then off the coast of East Antarctica in my various trips down there. Here's the northern cryosphere. It's sort of the geographical opposite. Instead of a continent surrounded by oceans sitting on the pole, in the north we have the Arctic Ocean sitting on the pole, surrounded by the continents of North America, Russia, Europe, and so on. The dominant land ice sheet in the northern hemisphere is this Greenland ice sheet, again, which is glacial ice that builds up over millions of years, and in fact, it's maybe 2 miles, in the Antarctic ice sheet is up to 3 miles thick, whereas the frozen Arctic Ocean is on the order of 1 meter thick, 2 meters, 5 meters, 10 meters, something like that, but a completely different scale compared with the great land ice sheets. Now, why study sea ice? Well, there's still a lot of it, even though it's melting. It covers 7 to 10% of the Earth's ocean surface. It forms the boundary between the ocean and the atmosphere in the polar regions, and as such, it mediates the exchange of heat, gases, and momentum between these 2 principal geophysical fluids, namely the ocean and the atmosphere. Here you see heat rising up through the ship's track. This is actually the lifeboat of the Aurora Australis, the Australian icebreaker that I've now been on 4 different expeditions on. And sea ice plays, both the freezing and the melting of sea ice play a major role in overall global ocean circulation. And as this thin frozen layer, sea ice is not only a sensitive leading indicator of climate change, but it's a key player, a dominant participant in Earth's climate system. Now, one of the main roles that sea ice plays is in reflecting incoming solar radiation during the polar summer. Now, this is measured by what's called albedo, which is the overall reflectance of the surface, and albedo is the ratio of reflected sunlight to incident sunlight. And whereas white snow and ice reflect most of the incoming radiation, ocean water or melt pools or water in general absorbs most of that energy. Here you see a classic white polar ice cap reflecting most of the incoming solar radiation. And here, if some of that ice is gone, a lot of that radiation is being absorbed rather than reflected. I was going to say, can we lower the lights a little bit, or that was? I'm sorry, lady. I'm not sure if you can. I just don't want some of these slides to be washed out.
Not much you can do with
Okay. Oh, there. Is that okay? Okay, that's fine. I think that's fine. Sorry. Okay. Okay. Just there's a lot of photos. I want them to show up properly. Okay. Let's see. So now, what's been in the news is the dramatic losses in the summer Arctic sea ice pack, and of course that's when the sun is shining. So this is important. So this dotted line here represents about a 20-year average of the extent in square kilometers of the summer Arctic sea ice pack. And you see that it's hovering around, at least in the early portions, hovering around 7 million square kilometers. But there's an overall downward trend, and then 2007 was sort of a watershed year when things really fell off the table. And it bounced back to this trend line, but then this last October, I believe it was actually September 13th, which was the day before we left on our most recent Antarctic expedition, we reached a new record minimum of about 3.5 million square kilometers. Although on that day, I believe these are monthly averages, but I believe on that day the extent of the Arctic sea ice was 3.41 million square kilometers, which means that you could make the statement we've now, over this, compared to this long-term average, we've now lost over half of the summer Arctic sea ice pack. So when you hear statements about, well, global temperatures have risen by a degree over 50 years or something like this, you can sort of, kind of ignore maybe what's going on with our climate. However, he's going to be my next field assistant. Where was I? Anyway, you see we've now lost a tremendous amount of ice, and we seem to be on an inexorable trajectory toward ice-free summers. Okay, so yeah, and I guess this is to follow up on this last point. When you hear about a change of a degree or something, doesn't sound so dramatic. But when you look at pictures like this, satellite images of the Arctic ice pack, this is back at the dawn of the satellite era with an extent of around this 7 million square kilometers. And then here, this is about half. So you see the dramatic losses that have been incurred. Sorry, my laser pointer is sort of not doing so well here. So let's see that. Okay. So this is actually predicted in the sense that what we're seeing is an example of what's called polar amplification. That climate change is actually amplified in the polar regions, and that warming is occurring at a much greater rate, a much faster rate than say in the equatorial regions, or for us, for example, in Utah. Now, one of the dominant mechanisms that's driving this incredible loss of ice and change of our climate, particularly in the polar regions, is that as you melt this ice back, so now instead of that white surface protecting the Arctic Ocean below from warming up and from absorbing radiation and further warming, well, now with that ice gone, instead of that ice, that solar radiation being reflected back into space, now it's being absorbed. So you're absorbing more solar radiation, warming the ocean further, and melting even more ice. And this is what's called the so-called ice albedo feedback. So you melt some ice, and this actually even happens on local scales, on these melt pools and so on. That's what helps to enhance the melting of the Arctic ice pack in the spring or summer period. So that lowers the albedo, and then you absorb more sunlight, which means you melt more ice, in turn lowering the albedo, absorbing more sunlight, and so on in this positive feedback loop. Now, when you look at photos like this, So actually, these are photos from the Antarctic that I've taken, and this is a photo from the Arctic. And actually, this is Amy Heaton, who was one of my, actually took Calculus 1 with me as a 17-year-old freshman, marched up to me and said, after one of my lectures, I sort of incorporated some sea ice into our calculus, and she marched up to me and said, I want to do sea ice for my undergraduate research. And lo and behold, she was my first student that I took up to the Arctic with me, and or even to the Antarctic. She was my first student I took up to the polar regions at all, and she became a co-author on some of my more important papers in this area. And so, however, when you look at these kind of photos, you might think that sea ice is just a barren, impermeable, frozen cap. However, in fact, when you look at the interior of sea ice on a fine scale, in fact, it's a complex, porous composite material consisting of pure ice with sub-millimeter scale brine inclusions shown here. Here's a scanning electron micrograph showing extremely fine structure there. These inclusions join up to form channels through the ice. This is a vertical cross-section. This is if you take a slice across here, this is what you'd see, this complex sort of drainage pattern type of features. And as you may imagine, fluid can actually flow through these channels and through the porous microstructure of sea ice. And the flow of fluid through the sea ice turns out to govern a broad range of climatologically and biologically important processes in the polar marine environment. One of the main ones is the evolution of melt ponds, because basically this darker water compared to this light, white, snowy surface ultimately determines the overall reflectance or albedo of the ice pack. And whether or not these ponds pool up or drain within a day or something is determined by whether or not fluid can flow through this porous microstructure. It turns out that the polar oceans in the Antarctic and the Arctic have the richest life in the oceans in the world. And in the polar regions, this sea life is supported by the algae that actually lives inside the sea ice in those fluid inclusions, and they get their nutrients through this seawater, nutrient-laden seawater percolating up through the sea ice. And there's a lot of other processes as well that are governed or mediated by the flow of fluid through the sea ice. So what's this talk about? Well, fundamentally, I'm going to tell you about how we're using mathematics of composite materials and statistical physics to study sea ice structures and processes, ultimately with the ultimate goal of trying to improve our projections and understanding of climate change. First, I'll talk on the smaller scale on the fluid flow through sea ice problem, and then how we're doing field experiments on the sea ice in the Arctic as well as the Antarctic to try to understand this better. And then we'll start moving up in scale to applying some of these ideas that we've developed here and looking at how that plays out in the properties of these melt ponds, which actually is one of the largest unknowns and one of the biggest challenges in climate science today, is trying to understand how these ponds work and how that ultimately determines the reflectance or the albedo of the overall ice pattern. And then I will finally, again, move up in scale or cut across scales and how we're using mathematics to essentially understand the effective properties on larger scales of the sea ice system. A couple of the key concepts that are in this talk: critical behavior, how small changes in a parameter of the system can result in very large or dramatic overall changes in the system. Linkage of scales, how do you incorporate small scale behavior into, for example, larger scale coarse-grained models of the climate system. Cross-pollination, this is really where the mathematics comes in. This is the power of mathematics. Cross-pollination, by cross-pollination I mean taking ideas from some seemingly completely unrelated subject in science, taking the mathematics from there and applying it to sea ice, for example. Or, vice versa, taking mathematics we developed for sea ice and applying that to some seemingly completely unrelated area and develop new information about a different area of science. And ultimately, in the context of sea ice, we're interested in developing rigorous representations of sea ice in climate models. Now, I've been very fortunate to entrain a lot of non-sea ice people in the math world and particularly University of Utah into my work. a number of faculty, both in mathematics as well as atmospheric sciences, electrical computer engineering, various postdocs I've had, graduate students. Many of these graduate students started with me as undergraduates in my Calculus 1 classes, or right now I have 300 Calculus 2 students, 4 days a week in 2 classes. And I've involved many undergraduates, probably something about 25 undergraduates I've had over the last 10 years or so, and I brought many of them to the Arctic as well as the Antarctic. And you can see this is highly interdisciplinary: chemistry, physics, electrical engineering, mechanical engineering, computer engineering, physics, and so on. And I have close colleagues at very close collaboration with the University of Alaska Fairbanks, their Geophysical Institute, Victoria University in New Zealand. In Australia, we go to Antarctica with aboard the Aurora Australis, and then also at the Cold Regions Research and Engineering Laboratory, which is near Dartmouth, where I did my undergraduate work. Okay, so I'm sure you've all heard of the IPCC Projections, the Intergovernmental Panel on Climate Change. These reports that we put out every 4 or 5 years to kind of give the state of our climate system. And while and these are basically running something like the world's 18 or 20 best climate models, and whereas all the climate models predict a general decline of the summer Arctic sea ice over the 21st century, as you see here. This is like an average of all the different models and sort of the ranges that you see. What's striking is that the actual observations, the real data of how fast the ice is actually melting, far outpaces the predictions of any of these models. So clearly we're not incorporating all the physics, we're not properly representing sea ice, we're not incorporating all the effects, such as ice albedo feedback and some of these issues that I've been discussing. Just a word about global climate models. So here you see the Earth and gridded up like in this nice lattice type of system there. In general, climate models are systems of partial differential equations derived from the basic laws of physics, chemistry, and fluid motion. They describe the state of the ocean, the ice, the atmosphere, land, and how they interact. And fundamentally, these equations are solved on 3-dimensional grids using some of the most powerful computers that we have on the Earth. Grids of the ice, air, ocean, land system you see here. But and this is one of the key points, with horizontal grid sizes of maybe 60 kilometers, 100 kilometers, or something like that. That's the smallest grid size the world's most powerful computers can handle at this point. But I was just talking about sub-millimeter scale brine inclusions and fluid flowing through, on the meter scale. These are called sub-grid scale processes. And one of the keys and one of the most important things to do is to try to, how do we incorporate those kinds of processes, parameterize them, or properly incorporate them into these much more coarse-grained models. In these big global climate models that cover the whole Earth, the sea ice components cover how ice thickness is distributed. Balance of force is basically F equals ma, but for sea ice, and there's lots of different components. It's very complicated. These are actually very complicated nonlinear partial differential equations. And then heat and radiation fluxes through the sea ice into the ocean and the atmosphere. Now, with all this talk of melting ice, who cares? Who cares if the Arctic sea ice disappears? Well, obviously these guys do. The polar bears, they live there, and they use the sea ice as a hunting platform. And when you saw those distances, say from Alaska to the nearest ice, in the middle of the summer, hundreds of kilometers, whereas it used to be that it was just, right there. The ice was right there. So you can imagine polar bears drowning. This is affecting polar bear populations. If you live underneath the ice, the whales, they care because they feed. Basically, they get one of their main sources of food is coming from what feeds on the algae that live inside the ice. And so this is actually a movie that maybe some of you have seen. It's a pretty cool movie. It was making the rounds on all the cable channels, called Big Miracle, and it takes place in Barrow, Alaska. And so I believe it was so this is actually a real photo, a real story. This is back in 1988, and these whales got trapped, I believe, in October, I think, because there was so much ice. There's just, the ice was there, and these whales just got trapped. But now you don't see anything like that now. It's just, at that time of year, there's just no ice even nearby. So this is certainly has an effect on whale behavior. Walruses use sea ice, again, as a platform to feed, and here you see a group of walruses, but they're having their problems. Anyway, I've read some other articles about just these groups of walruses up on, they're kind of all confused. They don't know what's going on. It's like, they don't know what to make of it in some sense. Oil companies care. The Arctic holds about 25% of the world's undiscovered oil and gas reserves. And in fact, our last trip to Barrow last May, we stay in a sort of an old dormitory type place. It's called the Gnarl Hotel, but it's really just kind of like an old 50-year-old rundown barracks of some type. And anyway, usually just scientists in there, but last time we were there were a bunch of oil workers basically getting ready to drill. So this is really taking place and really going on in the Arctic. Beyond the Arctic, there are lots of impacts. You start losing all that ice, and it's going to affect global weather, including us. Changes in precipitation and temperature patterns, storm tracks. One climate model predicts reduced precipitation in the American West. So our license plates, the Utah, the greatest snow on Earth. Well, 50 years down the road, will we still be able to have that moniker on our license plate? I would assume the Arches one will still work, but whether or not we still have so much great snow, that's a question. Now, also, as we're talking about all this melting ice, you might ask, well, does this contribute to sea level rise? Well, no, not directly. Sea ice, basically, as you freeze seawater, it becomes less dense and then it floats. And then when you unfreeze or melt it, which is unfreeze it, it goes back down. And sea level remains the same. And same with icebergs, because they're already floating. It's the great land ice sheets. When that water is transported from the land into the water through like icebergs or calving or these kinds of processes, that's what's affecting sea level rise. However, there are indirect effects. As you melt more sea ice, that means that you are further warming the ocean. And in fact, the interaction of these warmer waters with the periphery of the great land ice sheets represents one of the most significant possibilities for abrupt climate change in our climate system. And just to answer just the most basic question as well, as Earth's climate warms, why does sea level rise shown here over the 20th century? Well, the melting of the great land ice sheets, as well as thermal expansion of the ocean as it warms up and it just occupies more volume. Okay, let's focus on the smaller scale stuff. So the basic law for describing slow viscous flow in a porous medium is called Darcy's law, where you relate the average fluid velocity to the pressure gradient, and through a coefficient of, say, of fluid conductivity or something like this, which is the numerator is the so-called fluid permeability tensor, which can be different, how easy it is for fluid to flow in any particular direction, and the denominator is the viscosity. This is an example of sort of one of the main areas of mathematics that I come out of, where my background is, called homogenization, which is the mathematics for analyzing effective behavior of heterogeneous systems. So one of the key phenomena that controls the behavior of sea ice, and actually that I kind of discovered back in the 1990s, was essentially the on-off switch for fluid flow. And so there's this brine and this lace throughout the sea ice, and as the temperature of the ice warms, the brine volume fraction increases. And it turns out then that for brine volume fractions below about 5%, sea ice, columnar sea ice, the classic kind of congelation ice that grows in the Arctic, is the fluid cannot flow. And then for brine volume fractions above 5%, fluid can flow, and it's increasingly permeable as the sea ice gets warmer, or as the brine volume fraction increases. Now, it turns out, by coincidence, that this critical brine volume fraction of about 5% corresponds to a critical temperature of -5 C for a typical bulk salinity of 5 parts per thousand. Hence, this has become known as the rule of fives. And this rule of fives controls a lot of these very important processes. One of the key ones in the Antarctic is called snow ice formation, where seawater percolates up and floods the surface, makes it all slushy, and then that slushy mix freezes into new sea ice, rather than classic sea ice formation of just freezing down in the downward direction. And this actually accounts for about 25% of the ice that's produced in the Antarctic. So this is a very important process. The evolution of salinity profiles, convection enhanced thermal conductivity as you allow fluid to move around through the ice. that enhances thermal exchanges, as well as I mentioned before, the evolution of these melt ponds and the overall albedo of the ice pack. So the fluid flow through the ice, and then in particular this rule of fives, the on-off switch controls these processes as well as a number of other ones as well, such as gas fluxes and so on. I mentioned the algae that lives in the sea ice. Well, biological activity turns on or off according to my rule of fives. This is a very dramatic demonstration of this, sort of showing an algal bloom in the fall, and then as it's like convection induced nutrient replenishment processes, and then all of a sudden it cuts off. Basically, that was essentially when the layer that the algae were living in, when the temperature got below that critical temperature, they were essentially then living from that point on in impermeable sea ice. Okay, this is just a quick image of the sea ice ecosystem, how the killer whales will try to eat the penguins. The penguins will live off the krill. I think these are kind of like similar to brine shrimp, the little shrimp that we have in the Great Salt Lake. You know, I don't know too much about that. But, and then they feed on the algae that's inside the brine inclusions in sea ice. So why is the rule of fives true? Well, fundamentally, this is one of the areas of mathematics that I've worked in a lot, is called percolation theory, mathematical theory of connectedness. So you start, say, with in this case, a two-dimensional lattice. With probability P, a bond is called open, that's the black ones. This is about 1/3 of them are filled here. With probability 1 minus P, a bond is closed, that's the blank spaces. And here, this is an impermeable state where fluid might try to flow through, but it can't. There's no connected pathway. Of course, we're really thinking of an infinite lattice here, and whether or not there's an infinite pathway or an infinite connected cluster. And then here's a P equal 2/3 state where there is a pathway, and so the critical point for this system is called the percolation threshold, where you have the first appearance of an infinite cluster.